What is force? A force is an external cause that can change either the size and shape of an object or the state of rest or motion of the object. For example, if we press a soft rubber ball from two sides, its shape changes. Or on stretching a rubber string, its length increases. In the case of pressing the rubber ball or stretching the string, we apply force. Similarly, when we want to move an object, we apply force, and to stop that moving object again, we use the force. Sometimes force is simply defined as a push or pull of an object. When force moves an object away from something, that is a push. When force brings an object closer, that is a pull. Types of force. According to the application, the force is classified into two categories: the contact force and the non-contact force. Contact force. Any kind of force that acts on objects when they are in physical contact is called contact force. Such as reaction force, tension force, and frictional force are examples of contact force. When these forces are in action, they act on the object with physical contact. That is why they are called contact force. Non-contact force. Any kind of force that acts on objects when they are not physically in contact is called non-contact force. Such as gravitational force, electrostatic force, and magnetic force are examples of non-contact force. When these forces are in action, they always act on an object from a distance. That is why they are called non-contact force. We will know more about all these forces in another video. For now, we will only focus on the concept of force and its measurements. As we already know from Newton's first law of motion, an object continues to be in its state of rest or of uniform motion in a straight line unless an external force is applied to it. This clearly reveals the concept of force. But how can we measure it? We can measure force from Newton's second law of motion. But before getting into Newton's second law of motion, we need to discuss another concept, which is the concept of momentum. Concept of momentum. All objects have mass, and if it is in motion, it also has a velocity. The combination of this mass and velocity gives the object a dynamical property called momentum. The momentum of an object is equal to the product of its mass and velocity. That is, if the mass of an object is m and its velocity is v, then its momentum is mv. Let's understand the concept of momentum with an example. Suppose two similar trucks, one loaded and the other empty, are moving at the same speed. In this case, due to the mass of the loaded truck, its momentum is relatively high. Now, if two trucks have to be stopped at the same time, more force must be applied on the loaded truck than the empty one. Consider again that the two trucks have the same mass, but different velocities. In this case, the higher the speed of the truck, the higher its momentum. Now, if we want to stop the truck at the same time, more force must be applied to the faster truck than the slower one. So we see that the amount of force required to stop an object in a given amount of time depends not only on its initial velocity, but also on the combination of its mass and velocity, that is, its momentum. It is noticeable that the momentum of an object depends on both its mass and velocity. Mass is a scalar quantity, but velocity is a vector quantity, so momentum is also a vector quantity. It has both magnitude and direction. In the case of momentum, the direction of velocity is considered the direction of momentum. Now, if we talk about the unit and dimension of momentum, then the unit of momentum is equal to the unit of mass into the unit of velocity. We know in the SI unit system, the unit of mass is kilogram, and the unit of velocity is meter per second. So the SI unit of momentum is kilogram meter per second. Similarly, we can write the CGS unit of momentum as gram centimeter per second. The dimension of momentum is equal to the dimension of mass into the dimension of velocity. We know the dimension of mass is m, and the dimension of velocity is LT inverse. So the dimension of momentum is mLT inverse. Newton's second law of motion. Newton's second law states that the rate of change of momentum of a body is directly proportional to the force applied on it, and this change in momentum takes place in the direction of the applied force. If an object of mass m has velocity v, the momentum of the object is equal to mv. According to Newton's second law of motion, if force F is applied to the object, then F is directly proportional to d dt of mv. Here d dt is called derivative, which represents the rate of change of momentum. You can also represent the rate of change of momentum as m into v minus u divided by t, where u is the initial velocity and v is the final velocity of the object. However, now we need a constant to replace the proportionality symbol and place the equal sign there. This constant is taken here as k. So the formula is written as F is equal to k d dt of mv. Since the mass of the object is constant, the change happens only in velocity. Therefore, the force F is equal to k m dv dt. We also know the change in velocity is acceleration. Hence, we can write the symbol of acceleration a in the place of dv dt. Then the formula looks as F is equal to kma. If we take unit force, unit mass, and unit acceleration, then we get k is equal to 1. Therefore the final formula looks as F is equal to ma. This is the formula for the measurement of force, where force is related to mass and acceleration. Force is a vector quantity because it has both magnitude and direction. Newton's second law of motion gives not only the magnitude of force, but also gives the direction of force. According to this law, the direction of the applied force is the direction of change of momentum, or the direction of change of velocity, that is the direction of acceleration. Now, if we talk about the unit of force, then the unit of force is equal to the unit of mass into the unit of acceleration. We know in the SI unit system, the unit of mass is kilogram, and the unit of acceleration is meter per second square. So the SI unit of force is kilogram meter per second square. This unit of force is called Newton. Similarly, we can write the CGS unit of force as gram centimeter per second square. This unit is called dyne. Definition of 1 Newton. The force acting on an object of mass 1 kilogram, causing an acceleration of 1 meter per second square, is called 1 Newton. As we defined 1 Newton, similarly we can define 1 dyne as follows. The force acting on an object of mass 1 gram, causing an acceleration of 1 centimeter per second square, is called 1 dyne. The relation between Newton and dyne is as follows. 1 Newton is equal to 10 to the power 5 dyne. As we find the unit of force, similarly we can find the dimension of force. The dimension of force is equal to the dimension of mass into the dimension of acceleration. We know the dimension of mass is m, and the dimension of acceleration is lt to the power minus 2. So the dimension of force is mlt to the power minus 2. Verification of the first law from the second law. From Newton's second law of motion, we find that F is equal to ma. Now, if no force is applied from outside, there is no change in the velocity of the object. The object continues to move with uniform velocity. If the object is at rest, it remains at rest. This is Newton's first law of motion. Within Newton's second law of motion lies the first law of motion. But Newton mentions the first law of motion separately, mainly to establish the concept of the inertial frame of reference. Here, I want to clarify that the inertial frame of reference is not related to the acceleration. It only relates to the object that is in rest or moving with uniform velocity. If acceleration is considered in the motion of the object, then it is related to the non-inertial frame of reference. But in this frame of reference, none of Newton's laws of motion are applicable. I will deeply discuss the concept of the frame of reference in another video. So, stay with us.